February 1944, a gray afternoon somewhere in the vast expanse of western Ukraine. The winter cold has begun its slow release, and the earth beneath the frozen crust threatens to transform into mud. A German Tiger I tank, 88 tons of steel and engineering excellence, the embodiment of German armor doctrine and industrial achievement, moves slowly through the countryside. Its gun is formidable. Its armor is the thickest on the European continent. To German tankers, to German generals, to German military planners, this machine represents something approaching invulnerability. The Tiger has been in combat for nearly 2 years. In that time, German crews have learned what German armor can do. They have learned that it dominates every conventional anti-tank gun currently in Soviet service. They have learned that if they maintain tactical discipline and preserve their armor formations, they are nearly unstoppable. But what they do not yet know, what German intelligence has failed to comprehend with any degree of completeness, is that American ordnance designers working in laboratories and test facilities far across the Atlantic have been developing a munition that will fundamentally challenge every assumption underlying German tank armor doctrine. This munition does not exist in large quantities yet. American industry has not yet geared up to produce it at scale. But it exists, and it represents a technological response to a problem that has haunted American commanders since German armor appeared on European battlefields. How do you kill a Tiger tank? The history of German tank superiority in the opening years of the Second World War was, in many respects, a history of tactical and organizational innovation. German armor doctrine, refined through campaigns in Poland and France, had emphasized concentrated tank formations operating in coordinated tactical groups supported by air power and infantry. The tanks themselves, while sometimes inferior to Soviet designs in certain specifications, were operated within a framework of tactical organization and command structure that allowed German armor to achieve local superiority and to break through enemy positions with devastating effectiveness. The Panzer III and Panzer IV tanks that formed the backbone of German armor forces were competent machines, but they were not revolutionary. Their significance lay in how they were employed and in the sophistication of the command systems that coordinated their operations. But the character of German armor doctrine began to shift fundamentally after 1942. The experience of extended warfare in Russia, the gradual realization that blitzkrieg was not going to deliver quick victory against an opponent with seemingly inexhaustible reserves of manpower and territory, forced German military planners toward a different approach. If quick victory was impossible, then what mattered was the ability to sustain campaigns over extended periods, to defend against numerically superior enemies, and to inflict maximum casualties on opponents while accepting that territorial losses might be inevitable. This strategic recalibration led German armor development in a new direction, toward larger, heavier, more heavily armored tanks that could absorb punishment and provide firepower that could overwhelm enemy defenses through sheer destructive power. The result was the Tiger I tank, introduced into service in 1942. The Tiger represented a fundamentally different approach to tank design from what had characterized earlier German armor. Where earlier panzers had attempted to balance mobility, firepower, and protection, the Tiger accepted significant mobility compromises in exchange for armor protection and firepower that simply exceeded anything else on the battlefield. The Tiger's 88mm gun, adapted from a legendary anti-aircraft weapon, gave it firepower that could penetrate the armor of any contemporary tank at distances where most Soviet or British anti-tank guns were themselves vulnerable. The Tiger's armor, with slopes designed to deflect incoming rounds, was the thickest mounted on a tank anywhere in the world. German engineers calculated that the Tiger could engage enemy tanks from ranges where it was itself immune to return fire. In theory, a single Tiger could dominate an entire sector of a battlefield, forcing enemy forces to seek alternative approaches or to accept casualties in exchange for closing to ranges where anti-tank guns could be effective. The psychological impact of the Tiger on the battlefields where it appeared was profound and immediate. Soviet tankers, encountering the Tiger for the first time, reported in tones of something approaching despair that the machine seemed nearly invulnerable. Soviet 76mm anti-tank guns, which had proven effective against earlier German armor, bounced harmlessly off the Tiger's hull and turret. Soviet tankers learned quickly that if a Tiger was on the battlefield, the only viable response was to attempt flanking maneuvers, to get to the sides or rear where the armor was thinner, or to accept that conventional anti-tank tactics would not succeed. British tankers reported similar experiences. German commanders, aware of the psychological impact their Tiger tanks were producing, became increasingly confident that this weapon represented a fundamental shift in the balance of armored warfare. For American planners, the emergence of the Tiger posed a serious problem. American tank development had followed a different trajectory than German development. American doctrine, influenced heavily by what American observers believed they had learned from European armor campaigns, had emphasized relatively light, mobile tanks optimized for exploitation and breakthrough, rather than for direct engagement with heavy enemy armor. The M4 Sherman tank, which became the backbone of American armor forces, represented this philosophy. The Sherman was fast, relatively well-armed, available in enormous quantities, and capable of being transported by ships and trucks to distant theaters of operation. American military planners had calculated that numerical superiority, combined with the Sherman's reliability and the tactical flexibility that American doctrine provided, would offset any qualitative advantages that German armor might possess. The problem with this calculation became apparent as American forces began to encounter German heavy armor in significant numbers. The Sherman's 75mm gun, which had proven adequate against earlier German tanks, was significantly less effective against the Tiger. The Tiger's 88mm gun, by contrast, could penetrate Sherman armor at ranges where the Sherman's gun could not effectively respond. American tankers, faced with the choice of closing to shorter ranges where they might have a chance of penetrating German armor or maintaining distance and accepting that their fire would be ineffective, found themselves in a deeply unfavorable tactical situation. American tank commanders reported with something approaching frustration that the only way to reliably kill a Tiger was to achieve numerical superiority so overwhelming that German crews could be overwhelmed through attrition despite the qualitative advantages of their machine. But parallel to the concerns of field commanders, American ordnance planners were already working on a different approach to the problem. If the barrier to defeating heavy German armor was armor thickness, if the fundamental problem was that conventional anti-tank projectiles simply could not penetrate the slopes and thickness of German tank armor, then perhaps the answer lay in developing entirely different types of projectiles. American ordnance designers, working with the Army's Ballistics Research Laboratory, had become increasingly interested in a concept that had been explored in various forms by different nations throughout the war: the armor-piercing round that relied not on explosive force, but on kinetic energy delivered through a very hard, very dense material. The concept was not new. British ordnance designers had experimented with tungsten core projectiles. Soviet designers had explored similar ideas. But American ordnance engineers, having access to significant quantities of tungsten and having developed manufacturing processes capable of producing the extremely precise shapes required, began to pursue this approach systematically. The result was the high-velocity armor-piercing round, or HVAP ammunition. The HVAP round represented a fundamentally different approach to anti-tank warfare. Instead of the conventional armor-piercing shell, a relatively heavy projectile with a hardened steel core designed to punch through armor through force of impact. The HVAP round was significantly lighter and fired at much higher velocity. The projectile itself was much smaller in diameter, but was made from an extremely hard, extremely dense material, tungsten. The physics underlying the round's effectiveness were relatively straightforward. The smaller diameter and higher velocity created a pressure concentration on impact that exceeded the ability of armor steel to resist deformation. Where conventional armor-piercing rounds battered through armor through a combination of kinetic energy and material hardness, the HVAP round essentially punched through armor through focused pressure concentration. The HVAP ammunition began to be produced in limited quantities in 1943 and 1944. American armored divisions received allocations of the new ammunition gradually, with initial supplies being reserved for situations where the advantage of HVAP penetration was deemed critical. The problem that HVAP solved was significant. The round could penetrate Tiger armor at much longer ranges than conventional ammunition. Where a conventional 76mm anti-tank gun might need to close to relatively short range to achieve penetration of Tiger armor, the same gun-firing HVAP ammunition could achieve penetration at substantially greater range. This meant that American anti-tank gunners could engage German heavy armor from ranges where they were themselves less vulnerable to German fire. The first extensive combat employment of HVAP ammunition by American forces occurred during the European campaign of 1944. American tank destroyer units, which had been receiving the new ammunition in limited quantities, began to encounter German armor with increasing frequency as American forces pushed toward Germany. The shock that HVAP created when it began to appear on the battlefield was profound and immediate. German armor that American gunners had previously been unable to penetrate suddenly became vulnerable. German commanders, confident in the invulnerability of their heavy armor, began to report with alarm that American anti-tank fire was penetrating the frontal armor of their heaviest tanks. German intelligence, tasked with understanding this sudden shift in American anti-tank capabilities, began investigating the nature of the new American ammunition. What they discovered alarmed them profoundly. The HVAP round represented not merely a marginal improvement in American anti-tank capability, but a fundamental challenge to German armor doctrine. The round was effective not because it was larger or carried more explosive power, but because it concentrated its kinetic energy into an extremely small point of impact with extreme velocity. A German tank that had seemed nearly invulnerable to conventional anti-tank weapons was becoming vulnerable to the new American ammunition. German military planners, confronted with the reality of HVAP ammunition, were forced to reconsider fundamental assumptions about tank armor design. The calculations that had guided Tiger development, calculations that had established optimal armor thickness and slope based on the assumption that threats would come from conventional anti-tank rounds, suddenly seemed inadequate. How do you armor a tank against a threat that concentrates pressure in such a small area? How do you design armor protection against projectiles that were essentially hardened steel needles fired at extreme velocity? The German response to the HVAP threat revealed both the flexibility and the constraints of German military planning. On one level, German armor designers attempted to adapt existing designs to the new threat environment. Additional armor was added to existing tank designs. Supplementary armor packages were developed and retrofitted onto existing machines. German engineers calculated new armor thickness and slope specifications designed to provide better protection against HVAP ammunition. But these modifications revealed the fundamental problem. They added weight, which reduced mobility, which required more powerful engines, which required more fuel and resources at a time when German industrial capacity was already strained to its limits. On another level, German military planners pursued entirely new tank designs intended to defeat the American anti-tank threat. The Panther tank, which had been in development for some time, was refined specifically to address HVAP penetration concerns. The Panther was designed with sloped armor specifically calculated to defeat both conventional and HVAP anti-tank rounds at anticipated engagement ranges. The Tiger II, a heavier, more heavily armored successor to the Tiger I, was developed with armor protection calculated to be effective against HVAP ammunition. But these new designs represented enormous increases in cost, complexity, and manufacturing difficulty at a time when German industrial output was beginning to decline due to Allied bombing and resource constraints. What German planners were confronting, though they did not articulate it in precisely these terms, was that American technological innovation had shifted the fundamental calculus of armored warfare. The problem was not that American anti-tank guns had become more powerful. The problem was that American ordnance designers had approached the problem of armor penetration from a completely different angle. Where German designers had assumed that penetration power came from mass and explosive force, American designers had recognized that penetration power could also come from velocity, hardness, and pressure concentration. This represented not merely a better solution to the existing problem, but a solution that came from a fundamentally different way of thinking about the problem. The implications were profound. The HVAP round represented evidence of American technological sophistication applied to a very specific problem. It represented American access to critical materials, tungsten in quantities large enough to produce thousands of projectiles, that other nations did not have. It represented American manufacturing capability capable of producing the extremely precise shapes required for HVAP projectiles, and it represented American willingness to accept the cost of producing specialty ammunition in significant quantities, even when that ammunition was more expensive than conventional alternatives. German tankers, reading reports of HVAP effectiveness and understanding the implications for their own armor, experienced a profound psychological shift. The Tiger, which had seemed nearly invulnerable, was now vulnerable. The armor protection that had been the source of German confidence in armored engagements was now demonstrably inadequate against American anti-tank fire. German commanders, who had planned their armor tactics around the assumption that German heavy tanks could dictate terms of engagement, now had to accept that the tactical environment had changed. The evidence of HVAP penetration accumulated through 1944 and into 1945. Tank destroyed after tank destroyed bore evidence of HVAP penetration. The distinctive appearance of HVAP penetrations, small, clean holes through armor that conventional rounds would have produced larger, more jagged penetrations, became depressingly familiar to German maintenance personnel and recovery teams. The holes were so small that German tankers sometimes did not immediately realize they had been penetrated until internal fires or explosions revealed the entry point. The psychological impact of this realization, that protection that had seemed adequate was now inadequate, that armor that had been trusted was now unreliable, contributed to deteriorating morale among German armored personnel. For American tankers and anti-tank gunners, HVAP ammunition represented something different, evidence that American industry, despite the qualitative advantages of German armor design, was capable of developing solutions that could defeat German armor. HVAP represented American innovation applied to a specific tactical problem. It represented American confidence that technological solutions could be found to military challenges. And it represented American abundance, the ability to produce tungsten in significant quantities, the ability to design and manufacture specialized projectiles, the ability to allocate resources to solving problems that German planners might have simply accepted as inevitable limitations. The production scale of HVAP ammunition tells a story about American industrial capacity. By late 1944, American ordnance plants were producing HVAP ammunition in quantities sufficient to ensure that American anti-tank units had reliable supplies of the new ammunition. This represented not merely a marginal production commitment, but a significant allocation of tungsten supplies, manufacturing capacity, and quality control resources. German ordnance planners, aware of HVAP production capabilities, faced a deeply troubling realization. American industry was not merely matching German capabilities, it was exceeding them, and it was doing so in specialized ammunition categories that German industry had not even attempted to pursue with comparable emphasis. The technical specifications of HVAP ammunition, as it evolved through 1944 and 1945, reflected ongoing American refinement of the concept. The 76mm HVAP round, which became the standard anti-tank projectile for American armored forces, weighed approximately 7 pounds, but delivered such concentrated impact force that it could penetrate armor that a much heavier conventional round could not. The 90mm HVAP ammunition, used in the newest American tank destroyers, was even more effective, capable of penetrating German Tiger armor at ranges that German anti-tank defenses could not match. German responses to HVAP, while reflecting genuine innovation in armor design, ultimately proved insufficient to the challenge. The Panther tank, with its sloped armor designed specifically to defeat HVAP, provided better protection than earlier designs, but was still vulnerable to American anti-tank fire at certain ranges and angles. The Tiger II, the most heavily armored tank Germany produced, was better protected but remained vulnerable to HVAP ammunition, fired from close range. Moreover, the weight and complexity of these designs meant that they were produced in limited numbers. German industry could not produce Tiger II tanks at anything approaching the scale at which American industry was producing Sherman tanks and tank destroyers armed with 76mm and 90mm guns firing HVAP ammunition. The symbolic significance of HVAP ammunition extended beyond its purely technical characteristics. The round represented American willingness to consume rare materials, tungsten, for the sake of achieving marginal improvements in anti-tank capability. German planners, watching American ordnance developments with alarm, recognized that this was not the approach of a nation that believed it was losing the war. This was the approach of a nation that was confident enough in its industrial capacity and resource access to allocate scarce materials to solving very specific tactical problems. HVAP ammunition was expensive, it was complex to produce, it consumed tungsten that could have been allocated to other uses. But American military planners decided that the benefit, improved capability against German heavy armor, was worth the cost. The contrast with German ordnance development was stark. German ordnance planners, constrained by limited supplies of strategic materials, by declining industrial capacity, and by the growing diversion of resources to air defense against Allied bombing, lacked the ability to pursue comparable innovation. German anti-tank weapons remained largely based on conventional design principles. German responses to American armor advances focused on armor design rather than ammunition innovation. This represented not a failure of German innovation, but rather a reflection of the different material constraints that German planners operated under. The HVAP round also became a symbol of American emphasis on technological solutions to military problems. Where German military culture often emphasized training, discipline, and organizational excellence, factors where German military planners believed they possessed advantages, American military culture increasingly emphasized technological innovation and industrial capability. HVAP ammunition represented the application of American technological sophistication to achieve tactical objectives that superior German armor design had made difficult to achieve through conventional means. The combat record of HVAP ammunition reveals its tactical and strategic significance. American anti-tank units equipped with HVAP ammunition reported dramatically improved effectiveness against German heavy armor. Tank destroyer units, which had previously suffered significant losses in engagements with Tiger tanks due to the inadequacy of their conventional ammunition, now reported achieving success against German armor that had previously seemed nearly invulnerable. These successes translated directly into improved American casualty rates and improved tactical flexibility. American commanders, no longer forced to accept that German heavy armor would dominate armor engagements, could make more confident tactical decisions about armor operations. Moreover, HVAP ammunition represented American capability to respond to German tactical innovations with technological counter-innovations. The Tiger tank had been developed specifically to shift the balance of armored warfare in Germany's favor. The HVAP round represented an American technological response that significantly mitigated the Tiger's advantages. This pattern of action and technological response would characterize the remainder of the European campaign. Germans would introduce new weapons or new armor configurations designed to provide tactical advantage. Americans would develop technological responses, often innovations in ammunition, gun design, or fire control, that addressed the German innovations. The result was an ongoing arms race in specific technical domains, but an arms race that increasingly favored American industry because American industrial capacity was larger and American access to strategic materials was more secure. The implications of HVAP ammunition extended beyond armored warfare. The successful development and deployment of HVAP ammunition demonstrated that American ordnance designers were capable of fundamental innovation in weapon system design. The round represented not merely an incremental improvement on existing designs, but rather a new approach to solving the problem of armor penetration. This capability for fundamental innovation, applied across multiple domains of weapon system design, would prove significant in post-war military development. American ordnance designers, having demonstrated the principle that armor-piercing rounds could be designed. Around hardened, dense projectiles fired at extreme velocity would continue to pursue this design philosophy in the post-war period. Many of the anti-tank and anti-armor ammunition designs that characterized American ordnance development in the Cold War era owed significant intellectual debt to the HVAP concept developed during the Second World War. German military historians, analyzing the course of the European campaign in retrospective studies, frequently identified HVAP ammunition as a significant factor in the deterioration of German armor effectiveness in the latter stages of the war. The confidence that German tankers had possessed in the invulnerability of their armor had been shattered by evidence that American anti-tank fire could penetrate armor that had previously seemed nearly invulnerable. This contributed to more cautious German armor employment and to reduced effectiveness of German armor formations. Moreover, the psychological impact of HVAP ammunition contributed to the general erosion of German tactical confidence as the war progressed. The availability of HVAP ammunition also provided American armor commanders with flexibility that they had previously lacked. American armor doctrine, which had always emphasized mobility and flexibility, could now be executed with reduced concern about German armor dominance. American tank commanders could engage German armor with improved confidence that their fire would be effective. American anti-tank gun crews could defend against German armor at ranges and angles that had previously seemed hopelessly disadvantageous. This improved tactical flexibility rippled through American military operations, contributing to better battlefield performance across multiple theaters. The contrast between HVAP ammunition and the conventional ammunition it supplemented tells a larger story about the nature of technological advantage in modern warfare. HVAP ammunition was not revolutionary in appearance or in the basic principles underlying its design. The concept of using hardened, dense materials for armor penetration was not new. The principle of firing projectiles at high velocity to achieve penetration was well understood. What made HVAP significant was not conceptual innovation, but rather the application of American manufacturing capability and American access to strategic materials to create a solution that was simultaneously elegant and effective. HVAP ammunition was the product of American industry at its best, taking known principles, applying them with precision and sophistication, and producing results that were operationally significant. For American ordnance designers, HVAP ammunition represented validation of an approach to weapon system development that emphasized technological innovation in response to operational challenges. The basic tactical problem, German armor that American conventional ammunition could not reliably penetrate, was posed by field commanders. American ordnance designers responded by developing a solution that drew on American technological sophistication and American access to materials. This pattern, operational challenge posed by field commanders, innovative technological response developed by ordnance engineers, improved field performance resulting from the new technology, would characterize much of American military development. The epilogue to the story of HVAP ammunition is written in the history of anti-armor warfare that would emerge after the Second World War. The principle that armor-piercing projectiles could be designed around hardened, dense materials fired at extreme velocity would remain central to American anti-armor ammunition design for decades. Cold War-era ammunition designs, kinetic energy anti-tank rounds using tungsten or depleted uranium cores, owed direct intellectual debt to the HVAP concept. The recognition that armor penetration capability could be achieved through velocity and hardness rather than through mass and explosive force would influence anti-tank weapon development across multiple nations and across multiple decades. The HVAP round also represented something more profound about the nature of technological competition in warfare. The emergence of German heavy armor, impressive and formidable though it was, did not represent an insurmountable technological gap. American engineers, given a clear problem statement, were capable of developing solutions that reduced or eliminated German advantages. This reflected not the superiority of American design genius or American innovation at some fundamental level, but rather the superiority of American industrial capacity and American access to strategic materials. American ordnance designers could afford to pursue solutions that German designers could not, because American industry could afford the cost of specialized ammunition production at scale. Moreover, HVAP ammunition represented American abundance applied to a military problem. American industry could afford to produce tungsten-cored ammunition that was significantly more expensive than conventional alternatives. American military planners could afford to allocate these expensive projectiles to field units, even when conventional ammunition might have sufficed for many applications. This reflected the reality that American industrial production was increasing rather than decreasing, that American access to strategic materials was secure rather than threatened, and that American confidence in the future trajectory of the war was such that investing in specialized, expensive ammunition seemed entirely rational. German tankers and German commanders, observing the effects of HVAP ammunition on their armor, understood that they were confronting evidence of American technological capacity and American industrial power. The Tiger tank, impressive though it was, represented a different approach to military technology, optimization within the constraints imposed by German resource limitations. American HVAP ammunition represented technology developed without such constraints, technology that reflected the ability to consume rare materials and allocate manufacturing capacity to problems that German planners might have simply accepted as unsolvable. In the small, clean holes that HVAP projectiles punched through Tiger armor lay evidence of a fundamental truth about the war, that American industrial capacity and American access to strategic materials had created advantages that German military innovation could acknowledge but not overcome. The HVAP round, in its small way, represented freedom and abundance applied to military technology. It represented the freedom to pursue solutions to problems that might seem impossible. It represented the abundance of resources and the sophistication of manufacturing infrastructure that allowed American industry to produce specialized,